thanks for inviting me. What I want to do, want to first give you a little bit an idea about embedded security from an academic, maybe also crypto point of view, similar to Kenny. My background is applied cryptography. Well, my background is applied cryptography, is doing real cryptography. And then I want to really talk about two case studies, namely cars and security, and also from a research perspective. And then I want to jump forward and look for more destructive aspects of IoT research. I mean, I want to look at low-level manipulation, so the dangerous things that can happen and that we researchers are working on. And then I have some advertisement slides at the end. So you all know that numbers. I saw that from this morning track, right? So we are, we're moving towards the IoT. And when was that? A few years ago, there was this critical moment where allegedly, I doubt everybody actually counted, but there were the equal number of connected devices than humans on planet Earth, right? So this is real. I don't know how accurate the numbers are, but this is a big thing, and that's why we're all here. So what is a question is, do we really need IoT security? And in the morning session, there were a lot of talks about how future system might look like, future IoT system, like smart city, blah, blah, blah. So what I think is interesting, let's look at here and now. Where do we have security issues here at this moment? And then more interestingly, how is IT security different from traditional network security? And in many respects, it's not. We heard about certificates. So there are many things, PKI solutions. There are many issues that are quite similar, but then there are also issues that are different. And this is what you're going to see on the next slide, where I looked at current type of systems that have security issues, I think, which are kind of unique to IoT. This is one thing that is often overlooked. This is a Amazon Kindle and an iTunes device, and they're embedded devices, they're IoT-ish, but their market success depends on digital rights management, right? You want to make it reasonably hard for somebody to buy a book at Amazon for $9.95 and to put it 5 minutes later on its own website, right, for everybody to download. So the business model, two of the most valuable companies in the world, right, depend on data security and some kind of embedded devices. So this is a non-scary scenario. This is a business case here, right? Now let's talk about scary stuff, right? Does anybody know this story? Yeah, Dick Cheney, my favorite vice president. So he had a pacemaker built in, and I heard that story from Kevin Fu, a colleague of ours from the US a few years ago, and I didn't really believe it because the story was too good to be true. It turned out it is true. So here's what happened. He got a pacemaker built in. These pacemakers can get software updates over the air, obviously, right? You don't want to have an open heart surgery just to do a software update. He asked a surgeon to disable this over-the-air function. Why? Because he was afraid of assassinations, by bad people when he's traveling internationally, that they update the firmware in the pacemaker and it would kill him. That's the story that I heard from Kevin Fu, and then a few years later, that story was in the New York Times because his heart surgeon wrote actually his biography. So this is this is very close to home, very personal, very embedded type of device, and security plays a big issue, right? I'm going to talk more about privacy and security in car-to-car communication settings. And my final thing, very down to earth, very real. When I flew into Heathrow this morning, I had to show my German ID card, and it was read out electronically, right? They're all equipped by chips. So what you see here, this is not very science fiction type of things. These are real devices that feel it now, and they do need security. And in most cases, security is quite critical for the success of these devices. So, and we worked on some of these issues. So what I want to look now is on this whole car issue. And again, we have very much, not very much, but I have a research point of view on that. So the big question is, who needs talking cars? And maybe we can play that video now here. So that's an intersection in Kentucky. There's nothing special about it except there's a car crash. You're going to see the same crash again from a different angle. So it's just fun to watch, right? So, you know, there's somebody, not somebody, this car, right, coming from the right-hand side. So he is missing the traffic light, right? He's drunk or whatever, right? So why is that a problem? It has to do with these numbers, right? In the US, we have more than 30,000 car fatalities per year. We all roughly know the number of people died at September 11th, right? There were 3,000 people. So roughly, you know, once per month, you have that many people dying in car accidents that died on September 11th, right? And we're not starting 3 wars every month, right? So this is really bad. EU is not much better, right? So we have around 30,000. It did go down, this number, but this is a different story. But it's similar numbers, right? So, I mean, it's, you know, in terms of human tragedies, this is bad. In terms of economic reasons, right? You know, there are billions of pounds or euros involved. So the question, how do we deal with that issue? You know, how do we get the numbers of car accidents down? Well, 90% driving errors, right? It's a really long time that my Volkswagen Beetle brakes didn't work, right? That was early 1980s. Cars have become really, really reliable. So what our colleagues from mechanical engineering did, they designed this unbelievable great system, right? ABS system, seat belts, what else do I have here? Airbags, right? So, but at some point, that's it. You can't get much better. At some point, you start fighting the physics, right? If you drive on German Autobahn with 150 kilometers per hour, there's only that much you can do. So what all the big car areas, which means North America, Europe, and Japan, and South Korea, now also China, betting on is electronic driver assistance, which is different from the autonomous cars that are now in the press almost daily. So this is more benign, simpler technology, but feeling that is still very hard. So what people want to do is they want to enforce car-to-car communication. It's a very simple system. You broadcast your position, and why greatly improve safety and improve traffic management. I have a former PhD student of mine. He's one of the top people in the US designing secure car-to-car communication. They estimate that, what is the number? I think they hope if every single car in the US is equipped with car-to-car communication, they want to get the number of deadly car accidents down by 75%. So going down from whatever, 30,000 to 7,500. Even if they're off by a factor of 2, right? We'd probably talk about 10,000 people lives saved per year, right? So this is, in terms of doing good things for the world, this is not the worst thing you can work on, right? Maybe more important than, you know, talking dishwashers or whatever, right? So, so I think this is a really good thing. And there are laws in place in the EU. I think by 2020, every single car that will leave the conveyor belt at Volkswagen at the end has to be equipped with this car-to-car communication. It's a very simple, relatively simple technology on a theoretical point of view. It's a variant of Wi-Fi, and what you do, you broadcast your GPS coordinates in a range of 300 meters, something like that. So very local, you know, you don't need new Bluetooth, blah, 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 blah. It's just your positions in all the cars. If you're a car yourself, you get all the GPS coordinates from all your cars in your surrounding, right? And then you can compute whether there's a collision imminent, blah, 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 blah. So if you look at that from a technical point of view, they're small messages. They're about 100 bytes. You know, again, just your GPS. The medium frequency, they're called sometimes the heartbeat messages. So every 100 milliseconds, 1/10 of a second, every car is sending out the coordinates. It's very ad hoc. You know, cars are coming and leaving, which is from a cryptographical point of view challenging because you have very short-lived security connections and you have to establish security connection rather quickly. But, and now it's getting interesting from an engineering point of view, even though you're only sending out maybe about 10 messages per second, you might be flooded with messages, right? Think LA highway, you know, whatever, 6 or 8 lanes in every direction. So you're talking about hundreds of cars. So it's something between 1,000 and 2,000 incoming messages that have to be processed. In terms of data volumes, it's not a problem because they're all short. But in cryptographic terms, this is a problem because every single message has to be authenticated. So otherwise you get another security problem in that, and there can be very simple attacks, right? Kids sitting on a bridge over German Autobahn and sending out fake GPS coordinates, and your car suddenly comes to a full stop, right? And then, you have a whatever 1.5 tons BMW sitting in the middle of the Autobahn, right? This by itself could be a huge safety risk. So what the standard's demanding is now that every single message is authenticated with a digital signature, which is a very, very standard tool, and Kenny can talk much more about it, which works beautifully, not beautifully, but it works okay on the internet. It's really hard to do here because you have this many incoming messages, and they have to be checked in real time. You can't do batch processing once a second, right? Because then the crash already happened. So how do we do that? And that was a research challenge when we were approached. And if you hate math, you can go to sleep for the next slide, right? This is really bad. Just want to give you a glimpse. So we need elliptic curves, which is the same type of crypto system that's used in Bitcoin nowadays. Just want to give you a rough idea what you have to do. You have to get this funny curve, and you have to do computation with these points, right? So you start with P, and you compute P plus P, and 3 plus P, blah, 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 blah. You do that S times, and you get this zero oval, which used to be a green oval, which used to be a green dot in my slides before I transferred them. And then for whatever reason, and you don't have to understand them, I just want to give you a glimpse that this is really complicated, right? Your public key is this green spot. So, these are two numbers that provides the coordinates of this green spot. And the number of hops, we started with P, 2, 3P, 2P, 3P, 4P, SP. This S is a private key, the secret key. This is the same thing happening in Bitcoin, or if you use WhatsApp, this is happening inside WhatsApp, right? If you do end-to-end encryption. So this public key cryptography. Again, and for WhatsApp, it's not a problem because you send a message, and you send a message maybe once a minute, and whether there is a half a second delay because your smartphone is doing cryptography, it's not a big deal, but in cars, it's a really big deal. So the challenge here is, the challenge is here, we have to do many, many, many computations to do that, right? And that's how we actually got in that game about 10 years ago, because people from the US approached us, said, can you do these computations? And these are a few billion multiplications per second, which was a real challenge a few years ago, at moderate costs. That was a problem, because in cars you have a very different cost structure than in computer systems, right? In Germany, there's this rule, everything that's more than, I think, 10 cents, that increase the car cost for 10 cents, needs the approval from the CTO of that company, Volkswagen. So that, they look at every fraction of a euro cent before they increase the cost, right? So the question is, how can we do this absurd number of crypto computation without buying a crypto accelerator, which sells for whatever, $200 at Amazon or so, right? And then we got into play, and we're looking at this low-cost Car2X security engine. And our solution, this was just prototyping, was we got away with about a $10 device, which was about a factor 10 better than what they had expected. We could do 1,500 signatures here. And it's used in, I don't know, maybe like 1,000 or 2,000 US field trials. Down the road, if that goes into mass production, they will get this $10 price tag down to way below $1 or £1 or €1 or whatever, right? So, but I wanted to give you an idea of what kind of challenges we can face in this consumer market, right? So high-speed cryptography. So now I want to look at a different case study, which is very recent, this new stuff we are working on. And this is not positively making products more secure, but looking at ways to make them insecure and maybe get an idea what kind of threats do we face that we also not really looking at right now. So typical task of researchers. We look at hardware Trojans. What are hardware Trojans? You have a given chip, and particular IoT devices, they're very often driven by real hardware chips, right? Many of them have software in, but many also have pure hardware engines in. A hardware Trojan is some kind of malicious manipulation of this chip. And what you see here, when you open up your laptop, or if I open up my iPhone 6, and there's some kind of main IC, and if I take sandpaper and I get rid of the coding, I see that, and that's probably a few 100 million of transistors, right? That's what you see on your iPhone. And a few billion if you open up your laptop chip, your Intel, right? So why would anybody maliciously manipulate that? Well, there are many applications for that, right? Application, the quotation mark. DoD is very worried about it. Underlying problem is that almost all chips are not manufactured in Europe anymore. They're almost all, I don't have the numbers, but something between 90 and 95% are manufactured in East Asia, including chips for US drones, right? So they are worried, DoD is worried that they order their chips, they get the chips back, they don't work properly. They might not work properly if the drone is over China or over Switzerland or Germany or England, whatever, right? And there are whole kind of abuse cases you can come up with. Maybe closer to home is critical infrastructure, right? Power, the whole power grid, smart grids, this is controlled by integrated circuits. Could be very interesting for an adversary to take control over our power chips, right? But also consumer device. Again, you can probably make even a business case, right? If there's maliciously manipulated iPhone or smartphone chips out there and somebody gets control over smartphones, right? So but how would that happen? You know, this is hardware manipulation, right? This is not trivial. One possible attack would be the scenario I sketched before during manufacturing, right? And these are, by the way, the new high-end chip manufacturing plants, the foundries, they cost around $10 billion a pound, right? They're super expensive. There are only a few left. This is one of the reasons why we can't do the chips anymore in England or in wherever, Scotland, Ireland, right? A little less not less science fiction, but less spy stuff is, again, if you open up your iPhone chip, you have this massive chip. This is not made entirely by Apple. There's something between 100 and 200 different blocks, hardware blocks that they buy from third-party vendor. Example is your Bluetooth interface, right? Apple is not providing the hardware for the Bluetooth interface. This is coming from somebody else, but it's all integrated in one chip. So one threat is that one of these 168 IP blocks is maybe malicious, right? It leaks crypto keys or it doesn't work properly, blah, 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 blah. Another attack vector is if you ship products and during shipments you have what NSA endearingly calls interdiction. So you open up the product and you swap hardware chips, you know, properly working hardware chips against hardware chips with a Trojan on it. But they can also build in by the manufacturer directly. You know, particularly if it's in your home country, maybe you can force the supplier to build in a backdoor, right? But it's really interesting. This is a relatively new area. I've been doing crypto hardware for more than 20 years. I'd never heard the term hardware Trojan until 2005. There was a Department of Defense, US Department of Defense, Science Review Board, and they really warned about the scenario. You know, the chips are manufactured overseas, people might build them Trojan, blah, blah, really dangerous for our military hardware, right? We don't know how realistic that scenario is. Ironically, what we know, thanks to Edward Snowden, is NSA is running these type of attacks, right? You know, these attacks, either interdiction, there's one confirmed case for that, but also built-in backdoors. It's very, very likely that NSA, and probably not only NSA, other intelligence services too, build in these Trojans deep, deep in the devices. And the scary thing with hardware is how are we going to detect them? And now I'm going to show you one case study how to actually do that, because the details can be quite tricky. So what we ask ourselves, how can we take a piece of hardware, manipulate it, but almost literally in an invisible way. So even if you open up the chip, you look at every gate, every transistor, every whatever function, it still looks perfectly good, but it's still Trojanized. So what we did, we looked at an inverter. So that's a very, very, very basic circuit element. You know, you get an input A, which is 0 or 1, and you invert it. Again, if you look at your Intel chip, you have a few millions of that. It's very, very basic element. So we want to do a relatively minor modification. We want to make sure instead of having this inverter property, we want to have a constant output, right? So what do? We look at, you see this yellow circle? So we look at this transistor, right? If you look at this transistor from the size, you get something like that. But this is blown up, right? And in reality, they're smaller, right? I mean, you know, this Moore's law, who knows Moore's law, right? These things are getting smaller. Do you see this gate thing, this orangey blocks? This is, when we talk about 12 nanometers, which is what Intel uses in the newest chip, this is 12 nanometers, and not, what is it? It's not 40 centimeters, right? It's tiny, tiny, tiny. So, and you have this orange p-doped areas where you put a few atoms with a different number of electrons in, right? This is the p-doping, right? So what we proposed, instead of p-doping, you do an n-doping, which is not a problem because 50% of the transistors are n-doped anyway. So you do an incorrect doping. If you do that, oh, and by the way, they're not orange and green in the real world, right? The atoms, you don't see them, right? And the concentration is like 1 in a million are these p-doped, right? So they're very rare and they're not colored, right? So they mean if you would look at that, they would look completely identical. So if you do that, you get this functionality, right? In the top, you get a closed transistor. You can do a similar trick with the bottom transistor, get an open transistor. So, and you get this functionality here. It's always on 1, right? So instead of inverting the input signal, you have a constant 1. It doesn't look very impressive here, right? So we have 2 questions now. Can this manipulation be detected? And actually, the harder question is, can we turn that into a useful Trojan? And, you know, useful in quotation marks from an attacker's point of view. So that's here my favorite slide. So one of these transistors, this is roughly what it would look like if you would reverse engineer that, if you would open a chip, which one has a Trojan in. You wouldn't find this as the same pictures here, right, that I'm using. So it would be deep inside, you know, kind of on the back of the screen, we would fiddle around with the transistor. So this is, it would be impossible to see, right? At least in the scenarios. Also meaning there have been there's a whole strand of research literature on detection Trojan. They're all going to fail in the scenario here. It's not impossible. I'm going to mention that towards the end of my talk, but it's very hard. So now the bigger question that I mentioned before, how do we exploit that, right? So we have now an incorrect functioning transistor, big deal. You know, how do we turn that into a security vulnerability? And then we had this really former PhD student of mine, Georg Becker, had this really good idea. We looked at the Intel TRNG. This stands for True Random Number Generator. So it gives you random bits. Why would we use that? Well, in particular for crypto keys, for things such as e-banking, right? Whole secure web browsing. Every time your little SSL symbol goes on your web browser, you need a cryptographic key that is typically is generated on chip from your Intel. And it's not only Intel, ARM has the same one in AMD, right? So now our idea is to manipulate this two random number generators so that you get, instead of, normally you can get 2 to the 256 different crypto keys, which is like the number of atoms in the universe, right? So there's no way to check for all keys. You get this huge number of keys, but with our manipulation, so again, what do we do here? So we look at the TRNG. This is now a transistor. This is a more realistic look, how modern transistors look. And you know, this is a substrate, you know, the silicon where we fiddle around with that. So now the idea is, instead of getting this huge, literally astronomically high number of keys, which nobody can check for, we try to strongly reduce the number of possible crypto keys that would be generated by your Intel processor, right? And one good example is, instead of we go from 2 to the 256 to 2 to 32 keys. 232 is a great number. It's a small number. It's 1 billion roughly, right? That means you can still have 1 billion different connections with Amazon.uk, right? You would use a different crypto key. That means it will not be recognized. Yet, as a designer, as a bad guy, you would know all of this 1 billion keys. And by the way, checking 1 billion keys takes maybe a second or a few seconds on your laptop, right? So this is a really good Trojan. Would go totally undetected, and it would be very, very bad, because whoever builds a Trojan in could break all secure connections that you have. It's also really scary because it's literally down, you know, and if you look at the system pyramid, right, up there you have the back end and the security architects, the crypto protocol, blah, blah, blah. On the bottom, you have your hardware, and it all hinges that the crypto works correctly. And now we're disabling the crypto, so to speak, because we know the cryptographic keys, right? So if this happens, it would be really scary. Of course, we didn't do it because Intel, you know, refused to collaborate with us. They hate us, right? This is really bad press for Intel, right? So, okay. So what is the conclusion from that? We got a lot of good press from that. The big lesson learned is, so in technical terms, yeah, you can build a meaningful Trojan, really dangerous Trojan without extra logic. It means detecting that is a very, very hard task. People have not really thought about it previously. Most detection techniques don't work, right? Well, this is rather technical. So this is the original paper that we had on that, stealthy dopant-level hardware Trojans. What is also interesting, we got, most people liked the work, but we also got some heat, as you know, people saying, oh, this is Christof, this is totally irresponsible, that, you know, the bad guys are being alerted, you know, about this really dangerous thing, blah, blah, blah. But why are we doing that as researchers? We want to find vulnerabilities, and then we want to build better system. And that did happen. That was only a year later. A strong team from Japan we weren't even aware of, they showed that, well, they're not quite as undetectable as we hoped. You know, this redoping, this green and orange zones, they can be detected with a, you know, run-of-the-mill scanning electron microscope. You can actually detect it. It's still a pain in the neck to do, but it can be done. And this is what we're hoping for, right? We show threats and say, well, this is really hard to detect. And then other good researchers go, it's not really that hard to detect. We can devise detection methods to check for these type of attacks, right? And this is what we're trying to do. So I think I have 2 final slides, or 3 final slides. So if you're interested in that stuff, with respect to cars, we've been running for almost 15 years. We've running the conference here in ESCA, Embedded Security in Cars, which just took place in Berlin. It's always in Germany, even though it's a very international conference. So if you're interested in car security stuff, also there's a lot of more like the business aspect of car security. Come to ESCAR, we get about between 250 and 300 people, and it's almost all industry. So the talks are semi-technical. I think they're very interesting. It's a very nice community, so I really enjoy being there. If you're more interested in the technical works that we're doing, and Meyer is going to talk much more about it in the next talk, our conference of Meyer and me is the CHES Cryptographic Hardware and Embedded System Conference, which also has been running for almost 15 years by now, no, almost 20 years by now, right? It will be in Amsterdam next year. So again, but this is highly technical. So if you hate engineering and math, don't go, right? But it's still a great conference. If you want to learn crypto, don't buy my book. There's my whole course. I have 2-semester introduction to cryptography. By me is on YouTube. They're quite popular videos that follow my large intro course with 200 students. It's based on my book. So if you're interested in learning cryptography, go to YouTube. And that's the end of my talk. Thank you very much.